Hi all, I am Aishwarya presenting you the topic Principles of Scalable Performance. In this presentation, we will be discussing about performance matrices and measures. It includes the subtopics such as parallelism profile in programs, mean performance, Amdahl's law, efficiency, utilization and quality. The second topic, parallel processing application. It includes massive parallelism for grand challenges. The next topic, scalability of parallel algorithm. Here we will be discussing the algorithmic characteristics. And the last topic, the scalability analysis and approaches. It contains the topic scalability matrices and goals. Performance matrices and measures. Parallelism profile in program. First one, the degree of parallelism. The degree of parallelism reflects the extent to which the software parallelism matches the hardware parallelism. The execution of a program on a parallel computer may use different number of processors at different time periods during the execution cycle. That is, for executing a program on a parallel computer, it may be using different number of processors at different time period during the execution cycle. And for each time period, the number of processors used to execute a program, it is defined as the degree of parallelism. That is, we here told that it for executing a program, it may take different number of processors at different time period. For each time period, the number of processors used to execute a program is defined as the degree of parallelism. This is the discrete time function assuming only non-negative integer value. And we can plot this DOP as a function of time. That is the plot of DOP as a function of time is called the parallelism profile of a given program. Next is the average parallelism. A parallel computer consisting of n homogeneous processors, and the maximum parallelism in a profile is termed as M. In ideal case, this n is the n homogeneous processors and M is the maximum parallelism in a profile. In ideal case, n greater than M. The computing capacity delta of a single processor is approximated by the execution rate without considering the penalties from memory access, communication latency, or system overhead. And when I processor are busy during an observation period, that is all the I processors are busy, we have DOP equal to I. And the total amount of work W performed is proportional to the area under the profile curve, that is W equal to delta integration of DOP T dt. Here the integration range will be T1 to T2. Mean performance. Consider a parallel computer with n processors executing n programs in various modes with different performance levels. That is, we will having n processor executing m programs in various mode with different performance levels. We want to define the mean performance of such multi-mode computer. With a weight distribution, we can define a meaningful performance expression. That is, here we will having an arithmetic mean performance and a harmonic mean performance. The first one is the arithmetic mean performance. Let Ri be the execution rate of programs, and here I equal to 1, 2, etc. m. The arithmetic mean execution rate is defined as Ra equal to sigma of I equal to 1 to m Ri divided by m. It is the arithmetic mean execution rate. The arithmetic mean execution rate is proportional to the sum of the inverse of the execution time, and it is not inversely proportional to the sum of the execution time. That is, the arithmetic mean execution rate is proportional to the sum of the inverse of the execution times. The second one is the harmonic mean performance. With the weakness of this arithmetic mean performance measure, we need to develop a mean performance expression based on the arithmetic mean execution time. That is, we have many weakness in the arithmetic mean performance. So we need to develop an arithmetic mean execution rate. In fact, Ti equal to 1 by Ri. It is the mean execution time per instruction for a program I. That is, Ti equal to 1 by Ri will be the mean execution time per instruction for a program I. And the arithmetic mean execution time per instruction is defined as the Ta. And the Ta equal to 1 by m sigma of Ti. So the harmonic mean execution rate across M benchmark program is thus defined by the fact RH equal to 1 by Ta. So far we told that the Ta equal to 1 by m sigma of Ti. So substituting this value in RH, thus it becomes m divided by sigma of 1 by Ri. Next one is the Amdahl's law. Assume Ri equal to 1, W equal to alpha 0, 0, etc. 0, 1 minus alpha. Here W1 equal to alpha, Wn equal to 1 minus alpha, Wi equal to 0, for I equal to 1 and I equal to 0. And this implies that the system is used as a pure sequential mode on one processor with probability alpha. That is, if the system having one processor, it will be in a pure sequential mode with probability alpha, or in a fully parallel mode using n processor with the probability 1 minus alpha. That is, if the system is using a n processor, it will be in a fully parallel mode with the probability 1 minus alpha. Substituting R1 equal to 1 and Rn equal to n and W in equation, we obtain the following speed up expression. Sn equal to n divided by 1 plus n minus 1 alpha. This is known as the Amdahl's law. And the implication is that S tends to 1 by alpha as n tends to alpha. In other words, under the above probability assumption, the best speed up one can expect is upper bounded by 1 by alpha, regardless of how many processors are employed. That is, the best speed up we can expect is upper bounded by 1 by alpha. Efficiency, utilization and quality. Here first we will be discussing about the system efficiency. Let big of n be the total number of unit operation performed by an n processor system. That is, big of n is the total number of unit operation performed by the n processor system, and the T of n be the execution time in unit time steps. And the speed factor is defined as S of n equal to T of 1 divided by T of n. That is the speed of factor S of n equal to T of 1 divided by T of n. And the system efficiency for an n processor system is defined by E of n equal to S of n divided by n. Here the S of n is the speed up, that is E of n will be S of n divided by n, speed up divided by n processor, that is number of processors. And the efficiency is an indication of the actual degree of speed up of a performance achieved as compared to the maximum value. That is the actual degree of speed up of performance achieved compared with the maximum value is the efficiency. Next one is the redundancy and utilization. The redundancy in a parallel computation is defined as the ratio of big of n to big of 1. That is redundancy R of n equal to big of n divided by big of 1. The ratio signifies the extent of matching between software parallelism and hardware parallelism. The system utilization is in a parallel computation is defined as U of n equal to R of n into E of n. That is equal to big of n divided by n into T of n. The system utilization indicates the percentage of resources that kept busy during the execution of a parallel programs. It is interesting to note that following relationship 1 by n less than or equal to E of n less than or equal to U of n less than or equal to 1. That is the system utilization indicates the percentage of resources that kept busy during the execution of parallel algorithm. That is the percentage, how much resources is kept busy during the execution of parallel programs. Next is the quality of parallelism. The quality of parallel computation is directly proportional to the speed up and efficiency, and it is inversely related to the redundancy. That is the quality is equal to Q of n equal to S of n into E of n divided by R of n. That is, it is directly proportional to speed up and efficiency, and it is inversely proportional to the redundancy. It's about efficiency, utilization and quality. Next we have parallel processing application. Massive parallelism for grand challenges. The definition of massive parallelism varies with respect to time. Based on it will be changing by time. Based on today's standard, any machine having hundreds or thousands of processors is a massively parallel processing system. That is, if a machine having n processor or 1000 or 100 processor, it is known as the massively parallel processor system. Grand challenges. Now here we are going to discuss some challenges. We review below some of the grand challenges identified in the US. The first one is the magnetic recording industry relies on the use of computer to study magnetostatic and exchange interaction in order to reduce noise in metallic thin films used to code high density disk. That is the magnetic recording industry. It is using this computer to study about the exchange of interaction and all to reduce the noise in the metallic thin films used in the code high density disk. The second one is the rational drug design is being aided by computers in search of cure for cancer, acquired immunodeficiency syndrome and other diseases. That is, using a high performance computer, new potential agents have been identified that block the action of human immunodeficiency virus produce. That is, it is used in the rational drug design by the computer used by the computer in search of many diseases for cure for many diseases. The design of high speed transport aircraft is being aided by computational fluid dynamics running on supercomputers. That is, many transport high speed designing of high speed transport aircraft is being aided by computational fluid dynamics running on the supercomputers. Fuel composition can be made more efficient by designing better engine model through chemical kinetics calculation. And the next one is the catalyst for chemical reactions are being designed with the computer for many biological processes which are catalytically controlled by enzymes. Next one is the uh, ocean modeling cannot be accurate without supercomputing MPP system. And also the ozone depletion and climate research demands the use of computers in analyzing the complex thermal, chemical and fluid dynamic mechanism involved. And next, the sixth one is the other important areas demanding computational support include digital anatomy in real-time medical diagnostic, air pollution reduction through computational modeling, the design of protein structure by computational biologists, etc. So these are the some of the grand challenges. Um, one is the magnetic recording industry relies on the use of computer to study about the exchange interactions and all. The second one we discussed the rational drug design is used using this computer for cure of cancer and some diseases. And in the designing of high speed transport aircraft is being aided by computational fluid dynamics running on a supercomputer. And we discussed the catalyst for chemical reactions are also being designed with the computer. And the fifth we discussed the ocean modeling cannot be accurate without this supercomputing MPP system. And the last we discussed some of the areas is computer support in digital anatomy in real-time medical diagnostic air pollution etc. It's all about it. And next we have this scalability of parallel algorithms. Here we uh, we are discussing about the algorithmic characteristic. We summarize below some important characteristics of parallel algorithm which are machine implementable. First one is the computational granularity. The granularity decides the size of data items and programs modules used in the computation. That is, the size of data items and programs modules used in the computational is the computational granularity. Second one is the parallelism profile. The distribution of degree of parallelism in an algorithm reveals the opportunity for parallel processing. That is, how much the degree of parallelism in an algorithm reveals the opportunity for parallel processing. It is the parallelism profile. Next is the communication patterns and synchronization requirements. Here, the communication patterns address both memory access and inter-process communication. The pattern can be static or dynamic depending on the algorithm. The synchronization frequency often affect the effective efficiency of the algorithm. It's about the communication patterns and synchronization requirement. Uh, Next is the uniformity of the operation. This refers to the type of fundamental operation to be performed. That is about the uniformity of the operation. That is the type of fundamental operation to be performed. Obviously, if the operations are uniform across the dataset, the SIMD processing or pipelining may be desirable. The last is the memory requirements and data structure. In solving a large scale problem, the data set may require huge memory space. The memory efficiency is affected by data structures chosen and data movement patterns in the algorithm. Both time and space complexity are the key measures of the granularity of the parallel algorithm. That is, depending upon the problem size and the data set may require huge memory size. The memory efficiency is affected by data structure chosen and data movement patterns in the algorithm. It's all about the algorithmic characteristic. We discussed that what is computational granularity, uh, parallelism profile, communication patterns and synchronization requirement, uniformity of the operation and memory requirements and data structures are some of the algorithmic characteristics. Next is the ISO efficiency. The workload W of an algorithm grow with the S. S is the problem size. Thus we denote the workload W equal to W of S as a function of S. That is because the workload W of an algorithm grow with the problem size. So we denote this workload W equal to W of S as a function of this S. And the term ISO efficiency concept, it is this concept is relating to the workload to machine size n needed to maintain the fixed efficiency E when implementing a parallel algorithm on a parallel computer. That is, ISO efficiency is relating to the workload to the machine size n needed to maintain the efficiency E when implementing a parallel algorithm on a parallel computer. And here the H is the total communication overhead involved in the algorithm implementation. And here the the communication overhead is usually a function of both machine size and problem size. Thus, we can denote it is H equal to H of S comma N. The efficiency of a parallel algorithm implemented on a given parallel computer is thus defined as E equal to W of S divided by W of S plus H of S comma N. Here, the W of S, the workload corresponds to the useful computation, while the overhead, the total communication overhead is the H of S comma N are the computation attribute to the synchronization and both data communication delays. Here, WSS is the workload and H of S comma N is the total communication overhead are the computation attribute to synchronization and data communication delays. The overhead increases with respect to both increasing value of S and N. Next is a scalability analysis and approaches. The performance of a computer system depends on a large number of factors, all affecting the scalability of performance computer architecture program involved. That is, large number of factors are affecting the scalability of computer architecture program involved. The simplest definition of this scalability is that performance of computer system increases linearly with the number of processors. If performance of a computer increases linearly with respect to the number of processors used for the application. If the processors used in the application increases, its performance also being increases. It is the scalability. And scalability matrices and goals. Scalability studies determines the degree of matching between the computer architecture and an application algorithm. For different paths, the analysis may be end with a different conclusion. That is, a machine can be efficient for one algorithm and a machine can be bad for another. It may be depending upon the condition. And next we have The scalability matrices identified below are the some matrices affecting the scalability of a computer system for a given application. The first one is the machine size n. Here, the number of processors employed in a parallel computer system. It is the machine size. Number of processors employed in a parallel computer system. A large machine size implies more resources and more computing power. The second one is the clock rate. The clock rate determines the basic machine cycle. We hope to build a machine with a components driven by clock which can scale up with a better technology. And the next one is the problem size. The amount of computation workload or number of data points used to solve a given problem. It is the problem size. S is the amount of computation workload or number of data points used to solve a given problem. The problem size is directly proportional to the sequential execution time. And next is the CPU time. The actual CPU time elapsed in executing a given program on a parallel machine with n processors collectively. It is the CPU time. That is the actual CPU time elapsed in executing a given program on a parallel machine with n processors collectively. That is actual CPU time for executing a program. It is the CPU time T. Next is the I/O demand D. The I/O demand in moving the program data and result associated with the given application run. It is the I/O demand. That is for moving a program data and result associated with the application run is the I/O demand. Next is the memory capacity. The amount of memory used in program execution. It is a memory capacity M, the amount of main memory used for program execution. The memory demand is affected by the problem size, the program size and the algorithm and the data structure used. That is these factors, problem size, program size, algorithm, data structure all affect the memory capacity. Next is the communication overhead. The amount of time spent for inter-process communication, synchronization, remote memory access, etc. It is the communication overhead. That is, once more, the amount of time spent for inter-process communication, synchronization, remote memory access, etc. Next is the computer cost C. The total cost for hardware and software resources required to carry out the execution of a program. The last is the programming overhead P. The development of overhead associated with the application program. It is the programming overhead. So, we discuss some of the scalability matrices. They are machine size, clock rate, problem size, CPU time, I/O demand, memory capacity, communication overhead, computer cost and the programming overhead. So, hope you understand the topic. What is this principles of scalable performance and all of the subtopics discussed in this section. Thank you.